Good morning and welcome to another TPC Training webinar. Today we're going to talk about troubleshooting in all its forms, mechanical and electrical. Before we get going and I turn it over to your presenter, I do want to cover a few housekeeping items. The most common question we always get is, can I get a copy of the presentation? The answer to that is absolutely yes. At the end of the webinar, you'll receive a follow-up email with a survey on it to kind of tell us what you thought. And so please, if you want a copy of the webinar, just respond to that email and let me know that you want a copy of the slides, and I'll be happy to email those out to you. We will also have the webinar posted in a number of places. We'll have it posted on our YouTube channel, we'll have it posted on Vimeo, and we'll also have it on our website. So if you need to get a link to one of those, please let me know of that as well, and I will be more than happy to send that out to you, because we know that sometimes work gets in the way and people still want to be able to view the webinar in its entirety, so we can certainly help with that. We will do some questions and answers at the end of the webinar. You'll see on your GoToWebinar toolbar there on the right-hand side, there is a little question tab there on the bottom. Please enter your questions there, and we will answer those at the very end of the webinar, okay? So without further ado, I'd like to introduce Ralph Stevens to talk about systematic troubleshooting. Ralph?
Hi there, everybody. How are we doing? My name is Ralph Stevens. I'm going to walk you through this systematic troubleshooting webinar and stuff, and I know you're going to enjoy it because I enjoy doing it. So I'd like to thank you all for taking the time and being online to listen to this. And please, if you have any questions, please send them through. So who are we? TPC is the leader in industrial skills training and stuff. I know this because I've taken their classes prior to this, before becoming an instructor, and it's really, really good training. And believe me, when I'm one of those guys that I like the hands-on thing and stuff like that, and I want to know and I want to learn, and that's what you're given through TPC. All right, instructor-led training or live training. And online TPC training is a lot of really, really good courses that if you don't have the time to do a sit-down thing for 2 or 3 or 4 days or something, and you want to learn over time, the TPC online training is a really good opportunity to do that. And then we do have also TPC Operate, the next evolution of performance support, maintenance, repair, and operator-led training and stuff. And this knowledge transfer, because we have people out there who are retiring, such as myself. When I went to retire from my last position and stuff like that, they wanted to know what I knew, because when I left, there was going to be a hole, there's going to be a gap. There's something to think about when that's happening and stuff for your company and everything. So TPC Operate might be another opportunity for you to think about. So, like I said, the instructor today is myself, Ralph Stevens. I am a certified maintenance and reliability professional. I believe in doing the right maintenance at the right time and the right piece of equipment. Okay, and that's why I base my whole thought process off over. Got over 40 years in the electrical and mechanical field. We said I'm a certified maintenance reliability professional. I'm a certified wastewater operator and a collections operator and electrical operator. And like I said, I believe in doing the right maintenance at the right time, the right piece of equipment. And I make troubleshooting a fun game for myself, because otherwise I drive myself crazy, I'm sure. So today, in this webinar, we're going to cover systematic approach to troubleshooting, 3 stages of troubleshooting. Let's talk about determining a root cause of a problem and a motor pump combination on some electrical and mechanical issues, and troubleshooting essentials to get us through that. Talk a little bit about troubleshooting power distribution, troubleshooting some plant lighting, troubleshooting VFDs and PLCs, troubleshooting HVAC, and then we're going to talk a little bit about electrical preventive maintenance program. So first thing is, we have to develop a logical, systematic approach to troubleshooting. First of all, we have to confirm something's wrong, right? Is there actually, when I push the button, it's supposed to start, it doesn't start, oh well, let me call somebody, right? So your operator then has to have all the right training and skills and the knowledge in order to make his machine work, right? Let's say, I don't care if it's a piece of electrical equipment, mechanical equipment, air operation, hydraulic operation. We have to know how the machine is supposed to work before we can operate it. And I have to know how it works before I could troubleshoot it, right? So on my maintenance side of it, or troubleshooting side of it, whoever you send over still has to have that knowledge and skill. So a lot of times we do take operators to become maintenance field operators and stuff like that because they have that internal knowledge already. But it's important to have both of them on site in order to troubleshoot a problem. Very, very, like I said, got to confirm there's something wrong. Next thing is I always say use your senses. My first thing I always use is my common sense, all right? So a lot of times, I'm telling you, if it smells like something's burning, right? In wastewater, I was in wastewater and stuff like that, and I could usually walk into the building and take a good whiff, and I could tell you if the process is running good or not because of what the process is supposed to be doing, okay? That, and I use my sense, I use my hearing. I hear something clanking and banging that I haven't heard before. Walk into a room, walk into a mechanical room. I don't care if it's a boiler or anything hydraulic or something like that, or a card crusher. It doesn't really matter. If I hear something that I haven't heard first time, something's wrong. Something's wrong. Then we have to start digging into it and use our senses every single day. We have to gather our PPE. Safety has to be our #1 priority, okay? We cannot have people getting injured because of something we lack to give them or we lacked ourselves to do, right? Whether it be lockout, tag out, having the proper electrical PPE if we're working on something electrical to make an electrical safe work condition. That's a key thing for us and stuff, okay? So we got to make sure we gather our PPE. Next things, we have to get the prints and documentation. We don't have a print for our machine or our piece of equipment that we're trying to troubleshoot. We're going to be there a longer time. Eventually we could probably fix it, but got to have the print. We have to have an updated print, okay? That updated print should be marked with any kind of markups from, let's say it was installed in 2002, and I'm working on it today, and the print you hand me is from 2002. Am I really thinking that this print is the last and correct, most recent one? I'm going to say no, right? I'm going to say nobody's ever been in here before. Nobody ever changed a relay, maybe changed a wire around, maybe changed a hose if it's hydraulic or an air line's been changed or something like that. Or let's say, hey, 5 years ago they stopped making that part and we had to put a new part in, but we couldn't fit it in that area, so we had to move it over here, and we had to rewire it in some way, and we had to revalve it or whatever. All those prints should be updated, and I should have the most recent one in the pocket of the piece of equipment and either online for me and available to me. Let's say I don't have it. Documentation that I should have then is at least an O&M manual, an operation and maintenance manual, so that I can actually walk through it, read it, walk through it, and figure out, hey, this is exactly how it works, okay? And now, what's not working? And then I go to the part that I believe is going to help me out and figure this thing out. I want to develop a troubleshooting flow chart. Over the years, I've always, thought about this in different ways and everything, but just a regular flow chart, right? Yes, I go forward here. No, I go down and I check this. Think about how your machine's supposed to work. Get a logical, okay, I press the button, the pump turns on, and just, and then the fluid starts coming out, and the drill starts turning, and sequence of operation. Put that together in a flow chart, and excuse me. If it's yes, then we go to the next step. If it's no, where do I go and check it? So you can make these little flow charts like that, put them on the machine, have your operator help you with this because they know what's supposed to happen when, right? Timing of the piece of equipment. I don't care if it's I make a widget. That widget's got to come out every 5 seconds, let's say. Well, at second 3, it gets chopped in half or whatever it is. The operator's going to know that. And that's how you make up your troubleshooting chart. It's a flow chart. Then the first thing I always do on the electrical side of it, I test my incoming voltage and or pressure. Okay, so if it's a hydraulic and I need to have certain pressures, I make sure my pressures are there. If it's air, pneumatic, again, I check, make sure I got my pressures there and stuff like that. If voltage, I check for my voltage, all right? Then I check my outgoing pressures and or voltages and stuff. And that can be a pretty good indication. If I have everything coming in good and I have everything going out right, then I most likely have a mechanical issue. Okay, so that's the idea. That's the way I look at it and stuff. I get a different type of thought process. Then let's say pressure doesn't come out or voltage doesn't come out. Where does it stop? Because where it stops is a great place to start our troubleshooting idea of what is wrong with this piece of equipment. And normally, I'm going to tell you this right now, 99% of all of our failures are from something small, like a contact block or an ASCO solenoid or something like that. Once something fails, that part of the equipment is going to stop working correctly. But we have to know what that part of equipment does in order to troubleshoot. Okay, it's something to I know it's kind of a getting to know each piece of equipment is tough, right? Some of it has multiple pieces. That's why we rely on our operators, and that's why we have to take their knowledge and have to put into a book or something, or into a flow chart or something to say this is what it is. I would normally take the new piece of equipment came in and it's working all, the guys there who we bought it from and stuff, we set up the flow chart right then. I take my print, I go across the terminal strips, and I look at voltages. When I trace voltage to look at failures in my electrical system, all right? And that's, TPC trains you to do that. And we go through there and we sit there and say, okay, from neutral to pin 21, what do you have? And if you have voltage, that whole circuit's good, because we look at it in a ladder logic program of troubleshooting, okay? I would take my print, put into a ladder logic, all right? And by taking our class, we can show you how to do that. But you look at it and you go step by step, rungs of a ladder, okay? Where's my voltage come in? That's my first rung, all right? Where's my first master control relay? Second rung. And you draw it out this way, okay? And I take a highlighter then, and I every time get a copy of the print and my ladder logic thought process of troubleshooting, and I say to myself, hydraulically, electrically, pneumatically, no matter what it is, I go through there and I just, in my flow chart, I take it and I highlight it. And I say, okay, done, got it, done. This rung is done. Just a different way of thought process, okay? Then we have to find the problem or the bad device, okay? When we find that problem or bad device, then we take it out. And normally what I would do is I would test it first, all right? Test it, and I remove that device. I make sure that it is failed, okay? Because sometimes we don't want to be parts changers, okay? The idea is, yes, I know we're under the gun to get back in production, and we have all these things weighing on us and stuff, and time is money, and there's no product going out the door, all those sayings and stuff. That's great, but we can't rush, because how can I fix the problem? Let's just say I have a 11-pin relay that is burnt up, right? And I know it burns up every 3 months, right? And so I always carry an 11-pin relay in my pocket as a maintenance guy, and when it fails, I just go there, I pull the relay out, I stick the new one in, and they say, thanks, Ralph, you're the guy, way to go, you got it, and I walk away. I haven't fixed the problem. I band-aided it, I got it to work and everything, but I still now have to find out why this 11-pin relay is failing on me, right? And it's usually something that we rewired something, or we did something we shouldn't have done, because the manufacturer, whoever you bought this piece of equipment from, not going to make it let it fail in 3 months. All right, it should be a proven product. Okay, and so after that, like I said, you check that device, you remove the device, you test it, then you either replace it or repair it. Okay, and a lot of times, obviously, if it's there's a definite difference between NEMA and IEC products, and the NEMA product and stuff can be repaired. The IEC product normally has a chance to, most of the time we just throw it away, right? It's just cheaper for us. Then we have to confirm that the system is working correctly, okay? And now that's when we bring the operator back in, and or the maintenance guy, if he knows exactly what's supposed to, the widget's supposed to come out on that end, and this is the size it's supposed to be, and these are the cutouts that it's supposed to have, and or the electrical is, I turn this on, the motor turns on, then the pump turns on, and I get 60 PSI, I'm good. I know I'm good, okay? So I look at that, and I confirm that the system's working correctly. Then I could either fix or order a new device that I had to replace because I want to have that piece back on hand. Having spare parts, and you never think about building a spare parts inventory. A lot of us nowadays, we don't carry spare parts, okay? Or a different way of thinking it. When we have a course on reliability-centered maintenance, okay? Reliability-centered maintenance has us thinking in a different way. It has us putting the critical parts. We look at our process totally differently. We want critical parts, and anything that's critical to this piece of machinery that I just can't go down the street and buy, I want to make sure I have it on hand. So think about that. And like I said, the courses that we offer in maintenance, on the side of maintenance and stuff like that, and plant involvement in maintenance, totally, it's the spectrum has now changed. And it's a whole reliability-centered maintenance is all about reliability. I don't want to break down, okay? Got to have all my spare parts that I need that I can't get today on hand because that's money out of my pocket, okay? Think about that, all right? And then in the end, we have to complete the documentation. It's the key thing because I've just done something to this machine. I don't care if it's hydraulic, pneumatic, whatever, electrical, and I turn around and I did something, okay? Most of us, do we have a computer-based maintenance management system to where if I need something done to my plant equipment or anything like that, I get a work order and it's generated out of a program that somebody requested work and I send it out to them. If you have something like that, we must make sure that we're getting all the information back, not just, hey, complete, done, fixed, you name it, right? Think about putting more information in there about what you just did. What was done to this piece of equipment? This piece of equipment is, hey, guess what? It's I had to replace ASCO relay and the solenoid and stuff for it could have been electrical circuit breaker or whatever. All of that stuff becomes your spare parts list, right? Because think about it, that this thing's going to fail on you once a year and stuff like that, and I had to take it down for 2 days, wait for this thing to get ordered and stuff. That's how you build out your spare parts list, along with a history. And the history is really important because what did they do last time to fix this? I'm brand new on the job. I just got hired and stuff, right? The gent that was here either left, retired, is on vacation, whatever. And they're asking me to fix this. I don't have a clue about this machine. The operator's brand new, or he's on vacation or whatever, same thing. And my generalized thinking has to change. So what did we do prior to this? What was the problem before this, okay? So we have to complete the documentation so we can build a case history on all of our items that we do, okay? Even if it means filling out a piece of paper and sticking it in a book someplace and getting a log, everything about leaving a log next to the piece of equipment of what was done and how long it's been running and things like that. Different way of thinking, okay? So those are 15 steps I basically take to develop a logical, systematic approach to troubleshooting. Types of jobs that require troubleshooting could be anything, if you're a maintenance technician, and it could be anything on your equipment that you're running, your facility, overall facility, on the electrical end, for your operators. Let's think about, we got pretty much the same thing because the operator's got to work hand in hand with the maintenance technician, okay? Plant management, got to think about how do we want to troubleshoot. And like I said, keeping records and things like that, that's exactly what we need to do as plant managers. Engineering side and stuff like that, how about this? If you think about the reliability aspect and what parts you have to have on hand and what this system's going to do for you during your planning stage, you save a ton of money. This has been recorded throughout mechanical and electrical side of engineering. Another way of thinking about what we do and how we do it before we build it, really, and by getting everybody involved, and that's all the way down to the maintenance technician and the operator to say, hey, think about this. So what we're going to try and do, What do you think is going to help happen maintenance-wise or operator-wise to make it easier or better for you? Do you like this system? Give me your notes back, right? And then I'm actually going to read it as an engineer, okay? That's one of the main key things. And then everyone, this goes, you take these troubleshooting skills back to whether you're working on your car, or you're working on your sump pump in your house or anything like that, your furnace, it doesn't matter what it is. This is, you take it back home with you every day and you think about this every single day, systematic approach to everything we do. So again, equipment that needs troubleshooting could be a motor, a pump, or a blower, the electrical control panels, building automation, PLC systems. If you have a building automation system, you have a PLC in there, okay? And again, these are all things that TPC can help you train on and stuff like that. But the idea is that you have to start thinking about how the system works, all right? You got some crazy process out there, specific process equipment for your process whatever you're doing. Let's say if you have pH meters because you're doing something with water, okay? Those are critical parts to your system, okay? Am I adding the right chemical at the right time? Am I adding too much? Chemical costs me money. Am I adding too much? Okay? Just ideas. You got to throw out ideas. I love the brainstorming things where not just everybody in a white shirt or anything like that. It's everybody all the way down. Okay? And sit in a room, take your time, think about it. Okay? And let's just say the maintenance guy is having a hard time fixing it. Okay? The engineer or your foreman or your lead person or whatever comes in, they're having a hard time. Why not sit them all down together and say, hey, what are we doing? What's happening with the machine? Think about this, and have a little brainstorming session to help you get through a tight time. Right? Variable frequency drives. We don't do the proper maintenance to these things, just simple things like cleaning out the fan blower so it doesn't overheat and everything, not properly putting the right motor or the right size VFD to the motor, things like that. Just not hey, it works today. I don't really care if it works tomorrow. It's working today. I'm okay. Another thing we need to think about troubleshooting and stuff is making sure that the right equipment is based on the right piece of all the equipment throughout your process. All right. Don't undersize or oversize your motor. Doesn't make any sense. Don't undersize or if you need 50 gallons per minute of water, make sure you buy the right pump. That'll give you that, all right? The right VFD to control it, the right feedback processes so that it's going to work correctly for you, right? Emergency generators. How many of us have emergency generators? Think about, do we do maintenance to them? Huh? Some do, some don't, right? I've seen some where go in there, you open up the door and stuff, there's cobwebs all over the place. Well, it really doesn't run. I haven't used it in 3 years, okay? But do you maintain it? Nah, yes, no, maybe so. Or I call somebody. Do you know what they did? No, they just charged me. They changed the oil. They checked the batteries. Something that we should be testing all the time, right? So you need a program, and TPC can show you how to do that. Mechanical systems. Doesn't matter really what mechanical systems we have, whether it be a sub pump, fire pumps. Fire pumps got to be tested, right? So do you just let somebody come in here and do it? Do you have somebody walk with them? You have somebody verify to actually do what they're doing. That way, that person can then ask that outside personnel that's on site for them, how does this thing work? What do you do if this breaks? Or what do you, besides call you, what can I check before I call you? That's how you get a systematic approach to something that I don't really deal with this. It's only tested once a year, Do you know how to open up your elevator doors in case somebody gets stuck in them, right? Or do you just call the fire department? Or do you just, walk away, And it's kind of one of those things. You think about things before they happen. And on our mechanical system side, yes, we have hydraulic that we have to worry about, pneumatic, like I said before. These are all separate systems, HVAC, all separate systems that are going to affect us as we go through the day. So there's 3 stages of troubleshooting. Got to investigate the problem, Gotta have a clear statement of the problem. So somebody has to tell me what's wrong. Not just if won't start, doesn't work, you know. Then we have to identify to document the symptoms of it. Then we have to think about any recent changes to the system. Has anybody done something in the last 24 hours to create this problem down beforehand, right? Then we do an analysis, do some brainstorming, like I said. Then we think about what's the most likely causes, test some of these possible causes. Then we do implementation. We walk through this and say, okay, I've repaired the problem, verify the fix, and I document. This is how you build your troubleshooting charts, all right? Brand new piece of equipment comes in, I'm looking at all this stuff. I'm looking at brainstorming. I'm doing, okay, because inevitably, if we look at the O&M manual, in the back there, it says, hey, cause and effect, right? If this doesn't happen, check this. If this happens, check that. Well, I want to put that out front, because 3 o'clock in the morning, storm or whatever, or the plant's down, or my line is down. Am I going to go look in an O&M manual in the back and see what possible causes are going to give me this problem? Probably not. Okay. Then you got good questions to ask. You know, what am I trying to do? And this is what we talk to the operator and or another mechanic about, right? What did you see or hear when the fault occurred? Exactly when did it happen, the date and the time, right? And what should be happening when it was running? What was the process? What happened to the process? And what was anything changed in the system recently? And then, like I said, try to avoid yes and no answers. I need more detail, right? Yeah, it don't work. No, I don't know. You know, well, then we need to find somebody who does know, okay? And then you write all those answers down. I want to go back to them at a time, because documentation, like I said, we've been talking for 2 hours and we're trying to figure this out. And I say, hey, didn't you just say something about, yeah, I know, but I forgot. Yeah, let me think about it. Write it down. It's going to put you ahead, way ahead. Then we troubleshoot as a team. Like I said, we take the operator and the maintenance guy and or the engineering staff or the lead person, whoever it is, I need help, right? Because I want to bring up multiple ideas of what the problem could be, right? Especially if it's, you know, unknown or unfamiliar. Write those problem statements down, list the problems and what's most likely, and this part always comes easier, because as time goes on, you're gonna have different problems pop up and everything. And then we test each problem or solution until it's discovered. And then we verify the problem's been solved, and we document all that stuff again. Make a blog book. It's really simple. It's really a simple thing that can help you under duress. Because, hey, if there's an emergency and I need help, you know, three type of people. One person stands there and actually does it. Another person runs. The other person freezes. I don't know. I got nothing. What do you got? So we have to define the problem. This is the most crucial step. Is there really a problem? Like I said, my list our concerns. What are the problems? What choices need to be made? And what actions do we need to take? We want to clarify these. Got to be specific. Got to prioritize the problems and then think about the next step. Problems at what? At the system level, equipment level, or unit level, or the board module component level. So the system level is obviously, hey, I did something that a front-end batch, I put polymer in the system that was too thick to be pumped, let's say. Well, that polymer can't be pumped. It stopped my process down here, but it's a system problem, right? Then the equipment unit level, well, this piece of equipment, this pump cannot pump that polymer. Well, this is the system unit level now. And then I bring it down to the component level and or the board module level and say, hey, bad board, it's too thick to pump, so it jammed up the impeller or jammed up the rotor or something. That tells me I'm down to that component level. And then I make my fix. And I got two fixes here. One, I have to take care of my incoming polymer because it's too thick, and I have to fix my pump and or switch over to a backup and then fix this one later. But the idea is have to know what it is that's making the problem happen first, okay? And like I said, we always go to plan C, right? All right, so we got to develop a problem statement. The purpose of developing this problem statement is use a single statement. Think about it. Needs to include what, when, where, how, things like that. So is, you have two different thought processes, is and is not. So is, what thing or group of things is having a problem, and what is wrong with it? Now, on the backside of that, you're like, okay, what thing or group could be also a problem, and what could be wrong with them? Because then, okay, I know it's not that, it is, it's still this. So we have to develop a thought process, thought thinking, right? Where is the thing? Where was the problem noticed, right? And where is the problem located on your process, okay? And then you could say, well, where could be this? You know, this is not right here. It's farther down. And then when we troubleshoot and stuff, we look at. They always told us check the front end, check the back end, start in the middle. Remember that? So that's kind of what we do. Okay, machine's not working. Well, I got power and I got fluid here at the beginning. I have nothing at the end, so I go halfway and I check it again. And if I have it there, then I break it down to 3/4 or 1/4, depending on which way I have to go to see which way this problem is occurring. Then you have to say when. When was it first noticed? You know, when was there a pattern? Has this happened before? What's the history on this machine? That's when I look at my log, right? And then I could say, well, the problem is, this is the first time I ever had this problem. This machine's been running for 6 months, 24/7, and I walked in today and it wasn't running. All right, so how do you start? Okay, well, tell me try and start it. Well, that's the problem. I don't know how to start it. Oh, what do you mean? Well, had the training 6 months ago on how to start this thing, but it's been running. I haven't had, there's no reason for me to start it, so I forgot how to start it. And there's no book here? No, there's no book here. And so you step through this thing systematically, like I said, and figure it out together then. And then what's the extent of the problem? How many units do we, is it happening to more than one unit, right? And if it's not, if it is, it's a common problem, all right? We could make one repair here and make them throughout the whole subsequent units that are doing a similar action for you, okay? So developing possible causes. Knowing what possible causes or select comes from either knowledge or equipment and experience or identifying differences and changes. In order to do that, we have to eliminate causes that don't make sense, all right? As I said, use your common sense. If it doesn't make sense, can't. Forget about it. I push it off to the side, okay? Which of these possible causes is most believable, right? And then when presented with competing answers, one should select the one with the fewest assumptions, right? Common sense. Listen to your gut. Your gut usually is right, okay? Then we have to verify the cause. This is essential to avoid unnecessary fixes. And the following must be asked. Facts. How can we minimize and or check of our assumptions? Observation. How did we observe what we were thinking caused the fix or the problem? And research. How can we test what we think our cause is? We got to prove or disprove the theory of what we're thinking. And then results. How can we identify, in fact, that our fix is the fix? All right. Only make one change at a time, because if we start doing wholesale changes, hey man, it's got to be one of these three things. Just replace all three of them. Well, then you got three parts that you don't know if are good or bad. Okay. One step at a time. Check this. Pull it out, replace it, done. Okay, turn it back on. Still, it works better, but it's going farther down the function, but still not complete. So we got to still have a problem. Troubleshoot some more, find another device or problem fix, pull it out, replace it. Just think about what we do before we do it. That's the key. Then we select the fix. State the decision and keep track of it. We document it. This is what we did. You develop objectives. They could be multiple, all right? But each objective must contain an action that is observable or measurable for the fix, all right? Identify available resources, peoples, tools, parts. That's why I said if you have a book and you're following through and you're adding to it all the time, you're going to add operator observations, right? You ever think at the end of a shift and everything just anything happened? Nah, good. Why not put in there something like, hey, machine ran great, pressures. I read all my pressure gauges and stuff, and all my pressures were good, and I note my pressures. Gauge number 1 was 60 psi. Gauge number 2 was 5 psi. And because think about this, when something's not working right, and all of a sudden you say, hey, first gauge got 5 psi, it used to have 60, and now the second gauge got 60 psi, it should have 5. What do you think happened, right? So only real way to back that up is have documentation. Say what it should be. Because, hey, I never really look at the gauges. All I look at is the part coming out the end, okay? And then identify restrictions put on by us by laws, regulations, and policies. We cannot do something we're not supposed to do. Can't violate OSHA rules. Can't violate NFPA 70E, which are electrical safety rules. Can't obviously dump things into the sewer or something like that that might get us into having a problem with an environmental issue. Okay? And we must, like I said, state the decision and keep track of it. Classify objectives, mandatory, measurable, realistic. All right. If these 3 are met, this is a must objective. All right. Then try to think about beyond the initial fix. What caused the problem in the first place? All right. Like I said, that 11-pin relay that I was replacing, and walked in there every 3 months. Yeah, it failed. Okay, fine. I replaced it. It ended up being that there was a motor. They ran a 2 horsepower motor through it because 2 horsepower motor only took 5 amps, and the tips said that they were good for 10, but the tips aren't made to do a motor, right? So is that piece of equipment ready to do what you were asking it to do? Just because it's there and it's easy, we tend to do that, okay? We have to make sure that the problem's avoided in the future and have to be there for other fixes like this one on the other equipment. If I fix this one and I got exact same, if I have possible same problem on the next one, let's anticipate that, right? And do other equipment like this one need the same fix either now or inevitably in the future? So think about that too, is that somewhere down the line, if you have the same type of problem and you put together some type of matrix or something, or a thought process, have a talk, once a week, you ever think about taking 10 minutes in the morning and say, hey, what did we fix this week? What did you do? What was the problem, right? Get it out there and so we could talk about it, right? Then we have alternatives and risks. You have to consider alternative fixes. Can any of the alternatives satisfy our must or wants? And even if the alternatives aren't really used, keep track of them because they may be helpful in the future, right? If I need to get by, what can I do? I need to get by because I can't order this part for, 2 weeks it won't be here. I still want to operate. What can I do to get by? Have a bypass plan, okay? What if this thing fails? Let's say it fails and we did something and we jerry-rigged this thing to make it work for the next 2 weeks until we get the part, okay? We didn't bypass any safeties, can't bypass any safeties or anything like that, but we replaced this hose with a higher rated hose because we had one, and we're gonna make the fitting correct and everything else and fix this the right way, but right now this is a bypass for this, right? And on hydraulic line, let's say. That then could put into a plan saying, hey, we have spare parts here. Which spare parts are interchangeable? What can I use in order to make this work if I needed to, okay? Like I said, it's just a different thought process. And then obviously we have to consider the risks. When troubleshooting, there's always some type of risk assessment must be conducted every time. 3 questions we should be asking ourselves on any piece of equipment. Was it installed correctly? Yeah, no, I'm hoping, okay, don't know. Has been maintained properly? Even better, right? Because I should know that, right? And then is there any impending signs of failure, right? How's my housekeeping? Is this thing dirty all the time? Is it leaking, right? I just keep adding fluid because it's just dripping, one drip. It's dripping, 20 drips a day or something like that. It's okay. Think about that because the risk that you're taking, right? It's impendent upon us to have a job task plan, right? So you got to tell me what task you want me to do. You want to have a JSA or a job safety plan. And now we're required to do a risk analysis or some type of risk category of what you think could happen if it does happen, right? On the electrical side of it and stuff like that, a lot of us have little closets and stuff that have a lot of electrical equipment in there and stuff because it's easy, right? That's out of the way, but we put some shelves up in there above the electrical panels, put some paper products or whatever, and everything's good because it's also it's a storage room for my cleaning crew and stuff like that. That's not good, all right? We have to know if I'm going to be working on something, I need to know where is my shut off on this, because if electrically, if I get shocked and I can't let go, who's going to help me, right? Person standing next to me tries grabbing on me will get shocked. I need them to run back and turn the breaker off, right? So I got to know where the breaker's at. The way I look, it's my life too, you know. So I'm going to go into something like this. I have to look at the risk. What's the risk if I do something stupid? Okay. All right. And then how hazardous the fix is and how likely it is before the hazard to occur. So one thing we don't want to do is throw breakers and things like that on the arc flash side of it. On the electrical end, we do not want an arc flash incident. Okay. So we've got to make sure that everything is clean. We took all our tools out. Hey, just like the I saw the doctor left a tool in you, a sponge in you, his phone, right? It's not good after an operation, right? So you got to make sure that we get everything out of there and stuff. So when after you're done fixing everything, pull it all out. A lot of times the military has a board that all the tools that you took off have to be replaced where you can turn the machine back on. If the tools aren't back on the board, I know I left something in there, okay? We cannot leave things in a machine, okay? So here's a scenario, pump motor alignment scenario. Brand new pump motor assembly was just installed. The result of the bearings constantly needing to be replaced and the shaft run out issues on both the pump and the motor. The company higher up said, just replace it, don't worry about it, right? Rather rebuild it and keep doing this. It's not a good, run to fail is not a good concept, okay? And we can show you how, TPC can show you how run to fail is good for you in some instances and other ways not, okay? Upon removal of this pump assembly equipment was noticed the shims on the base, which are usually loose, not put in properly or something like that, right? And one of these shims particularly had a problem. So after installing, the contractor was brought in to conduct a laser alignment. And when he did this laser alignment and stuff, vibration analysis was done, and they were thinking about it and says, hey, guess what? It's misaligned. And it's because of coupling. Because the type of coupling that you use gives you a little bit of space to play with and stuff, but it might not be the right coupling. And that's why if something's failing constantly, you think about doing a root cause analysis and why it's happening. So you look at a root cause analysis. Again, is not, okay? What thing or group of things is having a problem? The same type of scenario we just talked about, we were going through, okay? Again, is it, what could be the problem? And we talk about this, we step this through it. Where is it? Where could be the problem? When was the first notice? When did you realize that you saw rubber coupling debris hanging out the bottom or being blown out of your machine and things like that? And then if applicable, we extend the extent of the problem. How many units do we have here that might have that problem? Shoot, you might have 50 pumps in your building, okay? So we start with a problem statement, all right? And it is or could not, but is not, right? Think about a problem statement. And we walk you through all of these. Motor showing high vibration could be misalignment. Where? On the motor side. On the pump side it could be, but it is not the pump side. Okay, then we know it's the motor side. When does it happen? Upon startup. When could it? It could be all during the whole time it's running. The extent, there's a long history of vibration and wearing out bearings, and the shims are rusted out. And that's probably not an issue with the pump, it's always with the motor. So that's how you do a root cause analysis. And we could step you through this, show you how to do it. And then the problem is, after laser alignment and upon startup, the motor is showing excessive vibration. So that's a problem statement, right? We step you through this. It's really a different way of thinking, okay? So if we're going to troubleshoot some power distribution, we want to talk about what is power quality in the industrial application. How does your plant work, and do you have any electrical issues? And then we would cover what problems are caused by poor power quality. You get harmonics, you get electrical troubles. Do you have a UPS in your system? An uninterruptible power supply. Then we give you some tips and tools to use, power quality meters and possible power correction units. Then we review the problems and work as a team to find out how to diagnose and correct the problem. Okay? Troubleshooting maintenance and plant lighting, or maintenance of plant lighting, right? Talk about lighting terminology, luminaire. And then we talk about troubleshooting and maintenance. What's the real difference between incandescent and LED? We talk about fluorescent lighting and HID lighting because those two are very prevalent in what we have in a lot of our facilities now, okay? And how to make them better for you and or make it easier to maintain. Troubleshooting HID lighting. If the unit's cycling on and off, it normally signals the end of life, okay? But it can damage your ballast if the lamp is not replaced in a timely manner. You always verify a proper match between lamp and ballast. HID lamps operate at really extremely high temperatures, and they're exercise necessary. The safety precautions on this is that, guess what? You cannot grab that, even with a glove, it's still going to be hot if it's on or cycling. Got to be careful you don't burn yourself. So you got to look about safety. Then we consider the use of a HID lamp fixture tester. Okay, and it's this one here, and then we show you, take this bad boy, you put it in there and stuff, it'll signal you as to what, if it's a starter, if it's a ballast, or the lamp, or a combination. Troubleshooting VFD and programmable controllers. Talk to you about VFD terminology and basic operation. We give you some common VFD problems and corrective action, and we look at PLC basics, ladder logic, and indications that help you in the field. Things to think about. Troubleshooting VFDs, troubleshooting checks. Got to check, we would check supply voltage, bus voltage, DC bus voltage. The motor, enable or permissive signals, runner start commands, and speed reference signals. If you have all those 6 checks, you win, right? And you could all, and we show you how to do it. We have this little star, VFD star thing that we talk about and stuff, but those 6 things happen. If you have that information, you could troubleshoot this VFD very simply, very easily. Then we give you these really nice troubleshooting guides and stuff like that. They're usually made in plastic, out of plastic embossed paper. Really good stuff. Gives you these little tips. And I would say to hang this type of paperwork at every workstation. Okay, this is troubleshooting. Think about what we're doing before we do it. Okay, ask the right question. That way I can give you the right answer. Troubleshooting programmable logical controllers or PLCs, give you an overview of PLC operation. We'll tell you what kind of types of PLCs, status indicators and error codes, and force and disable. These basic PLC items you should know about to help isolate your problem. And then you get some good specific PLC training. There's 5 parts of the PLC. Your CPU or your memory, power supply, inputs, outputs, and your programming device. Do you know what your lights mean when they come on? All right, so LEDs and stuff, they provide status indication to help us troubleshoot. Different manufacturers and models use different indicators. We help you walk through that. HVAC troubleshooting. Air conditioning and refrigeration cycles. We help you with this. We tell you what's supposed to happen when. Little things that happen. All right, a clicks on switch opens or something like that, and then gets reset because it cools off and stuff. Then it starts again. You're like, what the heck's going on? You have to understand how this system operates before you can troubleshoot it. We can help you with it. Again, you use the step-by-step logical troubleshooting chart and think about what this thing's supposed to be doing. Mechanical troubleshooting, we make observations. We look at mechanical faults. We look at suction and discharge pressure on HVAC to tell us what's going on with the system. We take temperature measurements. We take return air temperature, supply air temperature, suction line temperature, dish line discharge line temperature. Then we look at flow restrictions, external damage, dirt or debris, accessories, moisture, you name it. And we look at the power supply, controls and safety switches, system switch, thermostats, high temperature limit switch, low pressure switch, high pressure switch, access door switch, defrost controls, outside temperature switch. Now, if the access door switch has failed and nothing works, where do you even think about going to look for that, right? Then we give you some common things to think about. These are all the different items that are on a print that when we look on a print, we really don't know what they mean, okay? How many can you name, right? You're always looking at these things, and are they in the regular state? Are they in energized state? What does this mean? We give you all those definitions. We walk you through the problems. Successful electrical maintenance program. We discuss what programs you have in place. Do you have CMMS? Do you have data? What type of data collection do you have? Do you have a SOP? We look at additional technology you can use, such as an IR camera, handheld vibration monitor, conditioning bearing monitor. And we give you a whole bunch of different resources for that help. And TPC is a leader in training and operational excellence, hands-on and online resources. We're going to give you all that. So an effective electrical preventative maintenance EPM program terminology. Preventive maintenance, we tell you about what is really preventive maintenance. Conducting routine tests and inspections, that's what it is. And detect impending problems. Predictive maintenance. We talk about conducting diagnostic tests and inspections. We detect weaknesses and anticipate failure. Reliability centered maintenance. This is the new one, the key one. Right? Establishes your PM requirements based upon a consequence of equipment failure. You look at failure, look at the risk. What's it going to do to my machine? What's it going to do to my process? I have a plan, right? Electrical systems begin to deteriorate once they're installed. Performance and life expectancy of electrical equipment and systems decline because of environmental conditions, overload conditions, or excessive duty cycles. Principal reason for electrical system failure is a failure to maintain. Dependable designs require maintenance to keep them dependable. Failure rate is 3 times higher than electrical equipment that are not part of an electrical preventive program. And the risk of unscheduled electrical failure can be reduced by 66% with an effective PME. Fundamentals that we need to talk about is keep it tight, because vibration, expansion, contraction wrecks our system. Keep it dry, humidity, condensation, chemical, oils, causes accelerated oxidation processes and gives us failures. Keep it clean. Dirt, dust, lint, chemicals, metallic particles, oils, things like that, they clog our cooling systems and create fire hazards and increase resistance. And keep it friction-free. Prohibits free movement of electrical devices, increases arc flash hazards, and is very unforgiving. Develop a walkthrough inspection checklist. The purpose of this checklist is to help minimize the day-to-day electrical hazards. Based on Annex B of NFPA 70B, as in Bravo, and that's all about maintenance of electrical systems. The list is never complete, nor does the items necessarily appear in their order of importance. You can use this to develop your own plant-specific checklist. And we're here to help, right? We have a full suite of training options at tcptraining.com. We have upcoming seminar dates and locations near you at live.tpctraining.com, or you could schedule a site training at your facility at sales@TPC. Email us, please, at tpctraining.com. So, have any questions or so? And I'd like to thank you for your time, and I want you to work safely out there. I'll turn it back to John there and let me know.
All right, thanks very much, Ralph. A couple questions we're already getting are about getting a copy of the presentation. Yes, we can actually absolutely make that available to you. Please, when you get the follow-up email at the conclusion of the webinar, just respond back as a reply email requesting that, and I will send you out a copy of the PDF. Also, if you need a link to an actual recording of the webinar, I can provide that as well. Just let me know. So let's kind of go through the questions around here. Quick question is, do we have remote training? Yes, we do actually. We can provide training in an online module, so you can either do standard computer-based training, or we can actually do an online live instructor-led training as well. So you do have options there, but that is absolutely something that we provide. All right, so first question, Ralph. Can you use a meter to test a motor if it is bad, and how do you do that?
Okay, so you can use a meter to test a motor, but it only tests the wiring system inside, not the insulation. Most of the time what happens is a motor overheats and the insulation then breaks down and shorts to ground. A typical multimeter, let's say a Fluke or something like that, only has a 9-volt battery in it, and it will test the wiring side of it for you. But you really need to use a megger to put voltage to it, let's say 500 or 750 volts or 1,000 volts, depending on the type of motor. And using a megger, it tests the insulation value. And normally, the insulation will break down, and that's how the motor fails. That's the proper way of doing it.
All right, thanks, Ralph. Again, if you have any questions, please go to the question tab on the right-hand side of the GoToWebinar toolbar. Type in your question there, and please let us know if you have any questions. So we're still waiting on some more questions to come in. Ralph, do you have any parting thoughts or last-minute tips and advice for troubleshooting?
Yes, what I would say, take your time, know your system, and get help. Ask for it. Ask for training. Step out of the box. It's never, hey, I know what I'm doing, I got this, or hey, this is the way we've always done it and seems to work. Things like that. Think outside the box and stuff like that. Get the help that you need. We tend to think that asking for help is a weakness. It's not. It makes you stronger. I thought like that past history, right? Now I want the people around me to be smarter than I am. Makes us all look better. You have to work as a team, and that's part of it. It's part of getting everything together. And it's wonderful. Once you reach that plateau, it's a new way of looking at life. It's like, and when I retired and stuff from where I worked, it was I was thinking about that, and I said to myself, from where I started to where I ended up and everything, we made such giant steps together that we became a team. It was just not only me, and the same thing with troubleshooting or anything that we do in the business world or in the family life. Think about that, okay? Become a team, that's what I would say.
All right, thanks, Ralph. Next question, any recommendations for software for documentation and tracking of maintenance issues?
Sure. So there's a whole bunch of different programs out there and stuff. IBM makes Maximo, a little bit on the heavy side. SAP has one. There's another one called MainSaver. But you can go to any one of these trade shows now, and they probably have 30 vendors out there now that have Infotech. There's another one. There's a whole bunch of programs out there and stuff. But the thing is that don't just buy one to buy one. Buy one for what you need. And, because each one's going to have a specific thing. Like if you work on trucks or something, you want to know mileage and how much fuel they're using and stuff like that. Get one that's based more towards a trucking side of it or a vehicle maintenance side of it. Or if you're doing something that's more a production type thing, like MainSaver is made for GM, and I want to know when my widget was out of my box here so I can keep my machine, my line going. That works great for that. So there's a whole bunch of systems out there. You just have to see the one that you need, and always look at least 3 or 4 different ones, I would say.
All right, thanks, Ralph. Next question is, how do you check for amps on a motor?
Well, if you don't have an amp meter on the board there yourself, you can get a clamp-on amp meter, Fluke style, I would say, or something like that. You have to read the nameplate data of your motor. Let's say it's 20 amps at 460 volts or something. Carefully open up. You have to do all your PPE and lockout, tag out, and stuff, and set up your system correctly. but clamp onto any one of the three leads that are going out to the motor, and the meter is an inductance type meter, and it will read the amps for you.
All right. Thanks, Ralph. Ralph, could you put up in the beginning of the presentation, you talked about the 15 steps of troubleshooting. Can you put those slides back up real quick for us? We had a couple of requests for that.
Okay.
Oh, there it was.
Yep.
Any other, we'll leave this up for a couple of moments here so you guys can take a look at that, and we'll move on to some other questions. We had one question saying, I think this is a good introductory training for my team. Thank you. We agree. How do we have this particular training available in the future? This specific topic largely falls under a seminar that we call Troubleshooting Essentials, and we cover this in basically 2 days. So we basically compressed into 45 minutes what we would spend 2 full days working on. So if it sounds like we went through things pretty quick and kept everything high level, there's a very good reason for that. So if you do need a class like this, either in an open seminar format or even an on-site, we can certainly provide that to you. We can certainly touch base with that offline of this webinar to do that. But we can absolutely do this kind of a training in a longer, more in-depth format, certainly.
Mm-hmm.
All right, let's see if we got any more questions here. Ralph, how do you troubleshoot electrical components without it being under power?
Well, then you would use a meter and go the ohmatic value way. And when we show you how to do this too, but you would take and check each piece ohmatically, and each one of, whether it be a contact or a coil, they have different values and stuff, and we show you how to do that. And basically that's the easiest way to do it.
Okay. We got a question. What does PPE stand for? I assume personal protective equipment, right, Ralph?
That is correct, yes.
All right. Yeah, that's the clothing and gear you would use when working around electrical equipment to prevent arc injuries and basic electrical injuries that you can get as well.
Yeah, it's the three protectors are shock, arc flash, and arc blast.
Right. Ralph, if you're testing for amps and the 3 legs are different, does that mean more is going bad than what you may think?
Yes. So so it's a 3-phase motor, let's say, okay? And what happens is that whenever we do work, whenever you're asking a motor to do something, it's work. It heats up. It heats up the insides coils, and what happens is that the coils get too hot because you're asking to do outside its operational efficiency. Once you do that, the inside insulation starts to break down. When the inside insulation breaks down, the inner coils short together, and Ohm's law does not lie, the mathematical value of electricity, and as resistances change and or voltage and or amps change, one side's going to be off then from the other, so you know that's a really good way of looking preventative maintenance-wise what's happening with your system, and therefore you know you have a problem with that motor. They all should be within 10%. I always give 10% value, but 10% value difference. If I'm at 20, 21, and 30, I got a problem, okay?
All right. Thanks, Ralph. We want to be respectful of your time. We try to keep these to about an hour, so we have time for one more question. Ralph, does OSHA have any requirements as far as maintenance documentation?
They do to a certain extent. So OSHA looks at us in a couple different ways. Key, I think, for us to do document-wise and stuff is that we have to maintain all records of training. And so anytime anybody's been trained on anything, everyone must be trained or shall be trained, as according to OSHA, on every single piece of equipment that you have, and that has to be documented. OSHA also requires that we train, like if there's a meter on your maintenance staff is using some type of fluke or electrical meter, they have to be qualified in that. And we also have to qualify all of our personnel. So once you qualify them, you have to sign a piece of paper saying that they're qualified. And OSHA, we must maintain those logs for OSHA along with lockout tagout.
All right. Thanks, Ralph. Everyone, I do want to thank you again for attending the webinar. Just as a heads up, we will be having another 1-hour webinar coming up on September 21st, and this one's going to cover all things programmable logic controllers. So if you work with PLCs and you want to get some good info on that, we're going to spend an entire webinar just talking about PLCs. So please take a look out in your email for a registration on that one. But in that case, I will wrap it up. I do want to thank you again for attending the webinar. Please have a good day and work safely.
Thank you, everyone.